Black holes have long stood at the crossroads of science and imagination, embodying both the triumphs and the limits of human understanding. They are regions of space where gravity is so overwhelming that not even light, the fastest traveler in the universe, can escape their pull. At first glance, black holes seem like cosmic curiosities, strange byproducts of the equations of general relativity, too extreme to exist in the real universe. Yet over the past century, they have shifted from theoretical speculation to observational reality, becoming not only central characters in astrophysics but also cultural icons that challenge how we think about reality itself. Their very existence raises profound questions about the nature of space, time, and the ultimate fate of matter and energy. What makes black holes so mysterious is not only their extreme properties but also the veil they cast over what lies inside. The event horizon, the invisible boundary that separates the inside of a black hole from the rest of the universe, serves as both a literal and metaphorical barrier. Once something crosses this threshold, there is no turning back, no way for any signal or information to return. For an outside observer, this creates a paradox. What happens to all the matter and information that fall into a black hole? Are they destroyed, transformed, or somehow preserved in ways that we cannot yet comprehend? These questions do not just belong to the realm of abstract physics, they strike at the heart of our attempts to construct a coherent picture of the universe. The event horizon can be imagined as a horizon at sea. It appears as a boundary to our vision, a line that seems absolute but is in reality dependent on perspective and location. In the case of black holes, however, the horizon is not an illusion. It is a real surface of no return, marking the place where gravity bends spacetime so strongly that all paths point inward. To an observer watching from a safe distance, matter approaching the horizon seems to slow down, redshifting until it fades away. Yet for the falling traveler, the crossing happens in finite time, with no perceptible boundary at all. This duality in perspective is one of the reasons why black holes are such fertile ground for both scientific inquiry and philosophical debate. The central mystery that draws scientists and thinkers alike is what lies beyond the event horizon. Our current theories, built on the framework of general relativity, suggest that at the very heart of a black hole lies a singularity, a point of infinite density where the known laws of physics collapse. But infinities in science usually indicate a breakdown of theory rather than a final truth. This is why many researchers believe that the singularity is a placeholder for deeper physics that we have not yet discovered. Perhaps the key lies in uniting relativity with quantum mechanics, creating a theory of quantum gravity that could reveal the true structure hidden behind the horizon. Until such a theory emerges, the interior of a black hole remains one of the greatest unknowns in science, a blank space on the map of knowledge. Black holes are not only mysteries in themselves but also mirrors that reflect our limitations as observers. We are bound by the speed of light, constrained by the tools of measurement, and shaped by the theories that guide our interpretations. The event horizon symbolizes this boundary, a place where human understanding halts, at least for now. And yet it also inspires curiosity, driving us to question what lies on the other side. This dual nature, the horizon as both an end and a beginning, makes the study of black holes one of the most compelling frontiers in modern science. The fascination with horizons is not new. Throughout history, humans have looked to the edges of the known world and wondered what lay beyond. Ancient explorers sailed past familiar shores into uncharted waters, guided only by faith in discovery. Today, scientists stand at a similar threshold, gazing into the darkness of black holes and asking questions that might reshape our conception of reality itself. To better understand what lies behind the event horizon, we must first trace the path that brought us here, the centuries of thought, observation, and mathematics that gradually revealed these cosmic enigmas. And so, the journey into the mystery of black holes begins with the history of how we first came to imagine them. The history of black holes begins long before the term itself was ever coined, stretching back to an age when gravity was only starting to be understood as a universal force. In the late 17th century, Isaac Newton revolutionized science with his laws of motion and universal gravitation. For the first time, the heavens and the earth could be described with the same mathematics. The movements of planets, the fall of an apple, and the pull of the moon on the tides were all manifestations of a single principle. It did not take long for later thinkers to ask how far Newton's laws could be pushed. If gravity could act without limit, what would happen if a body became so massive and dense that its escape velocity exceeded the speed of light? In 1783, the English clergyman and natural philosopher John Michell proposed the idea of a dark star, a body so heavy that light could not escape from it. Almost simultaneously, the French mathematician Pierre-Simon Laplace entertained the same possibility. These speculations were remarkable in their prescience, though at the time they were little more than curiosities, since the wave theory of light and the lack of any observational evidence left such ideas without a firm foundation. For more than a century, Michel's dark stars remained a forgotten thought experiment, tucked away in the margins of natural philosophy. The concept lay dormant until the early 20th century, when Albert Einstein introduced a new vision of gravity. With the publication of the General Theory of Relativity in 1915, the universe was no longer governed by Newton's invisible force acting at a distance, but by the curvature of space-time itself. Mass and energy told space-time how to bend, and the geometry of space-time told matter how to move. Einstein himself was cautious about the more extreme predictions of his theory, but the equations carried within them the seeds of the black hole concept. Almost immediately after Einstein published his work, the German physicist Karl Schwarzschild found an exact solution to the field equations describing the spacetime around a perfectly spherical, non-rotating mass. This solution contained a peculiar surface, a radius at which the escape velocity equaled the speed of light. To a physicist of the time, it seemed like a mere mathematical oddity. Even Einstein doubted that nature could produce such extreme objects. Yet the mathematics was clear, and the Schwarzschild radius would later be recognized as the defining feature of the event horizon. Throughout the first half of the 20th century, black holes remained largely theoretical. The very name had not yet been invented, and most physicists regarded the collapse of a star into an infinitely dense point as implausible. The turning point came with the realization that massive stars could not always avoid gravitational collapse. In the 1930s, Subrahmanyam Chandrasekhar, then a young physicist, calculated the maximum mass that a white dwarf star could sustain before succumbing to gravity. Beyond this Chandrasekhar limit, no known pressure could prevent collapse. The idea was controversial and initially met with skepticism, including from figures such as Arthur Eddington. Nevertheless, Chandrasekhar's insight laid the groundwork for understanding the fates of the most massive stars. Soon after, other theorists built on these foundations. In 1939, Robert Oppenheimer and his student Hartland Snyder described how a sufficiently massive star, having exhausted its nuclear fuel, could undergo relentless gravitational collapse. In their model, nothing could halt the contraction once it began, and the star's surface would asymptotically approach the Schwarzschild radius, effectively creating what we now call a black hole. Oppenheimer and Snyder's paper, while technically sound, attracted little attention at the time. The Second World War and the focus on nuclear research pushed such exotic considerations to the background. For several decades, black holes were regarded as a mathematical curiosity rather than an astrophysical reality. The term black holes itself only entered the scientific and cultural lexicon in the 1960s, largely thanks to the American physicist John Wheeler. Before Wheeler, such objects were sometimes called frozen stars or collapsed stars, but these names lacked the evocative power that black hole carried. Around the same time, advances in radio astronomy and X-ray astronomy began to provide indirect evidence for the existence of extremely dense, compact objects. Observations of quasars, brilliant, energetic sources at the centers of distant galaxies, hinted at engines powered by supermassive black holes. In 1967, Jocelyn Bell's discovery of pulsars further confirmed that collapsed stellar remnants were real and observable, reshaping the field of astrophysics. The later decades of the 20th century saw an explosion of theoretical and observational progress. Roger Penrose and Stephen Hawking developed powerful mathematical tools to analyze singularities and space-time collapse, showing that under very general conditions, gravitational collapse to a singularity was inevitable. Their singularity theorems transformed black holes from speculative oddities into robust predictions of general relativity. At the same time, observational techniques continued to sharpen, leading to the identification of strong black hole candidates in binary star systems where one visible star seemed to orbit an invisible but massive companion. By the end of the century, the case was all but closed. Black holes were no longer merely the creatures of mathematics, but genuine astrophysical entities shaping galaxies and perhaps even the evolution of the universe itself. What began with Michel's conjecture of dark stars had matured, through the revolutions of relativity and quantum theory, into one of the central pillars of modern physics. The journey from Newton to Einstein and beyond is not simply a story of scientific progress, but a reminder that even the wildest speculations can sometimes find themselves reborn as fundamental truths about the cosmos. And it is at this point, with black holes firmly established as real, that the question of their inner workings, what lies beyond the event horizon, takes center stage in both science and philosophy. The idea of the event horizon is at the heart of what makes a black hole so different from any other object in the universe. In the simplest sense, the event horizon is the boundary that separates the inside of a black hole from the outside cosmos. It is not a solid surface like the crust of a planet or the blazing photosphere of a star. Instead, it is a mathematical surface defined by gravity, the precise distance from the center of the black hole where the escape velocity equals the speed of light. Once something crosses this boundary, it can never escape again. No matter how powerful a rocket or how bright a beam of light, beyond that horizon all trajectories curve inward. It is for this reason that the event horizon is often called the point of no return. The physical meaning of this boundary can be better understood through the lens of space-time, the four-dimensional fabric that general relativity describes. In everyday experience, we think of space as the arena where objects exist and time as the sequence in which events occur. Near a black hole, however, space and time are so dramatically distorted by gravity that their roles begin to blur. For an outside observer, time near the event horizon slows down to a crawl. A spaceship falling toward the horizon appears to move more and more slowly, its signals stretch to longer and longer wavelengths until they fade completely. To that outside perspective, the object never quite crosses the horizon at all, but instead seems frozen in place, smeared across the edge of the black hole. Yet for the unfortunate traveler aboard the ship, the experience is entirely different. They feel no abrupt change as they cross the horizon, and in their own time, the plunge into the depths continues smoothly. The paradox of two valid but contradictory perspectives is one of the striking features of general relativity, and it helps explain why the event horizon is such a rich subject of debate and fascination. To make sense of this for those not steeped in physics, it is useful to turn to analogies. Imagine standing on the edge of a vast waterfall. The river flows steadily toward the precipice, and once a leaf passes a certain point in the current, it is doomed to tumble over the falls. For an observer watching from the shore, the water just before the edge looks turbulent and stretched thin, but beyond the cliff it vanishes from view. The event horizon is like that edge. Outside of it, objects can still resist the pull, paddling against the current if they have the energy. Inside, the current is irresistible, and all paths lead downward. Another analogy comes from sound. Picture trying to swim away from a region where the water itself is rushing inward faster than any fish could swim. Just as no sound can escape the supersonic flow of air in a jet shockwave, no light can escape the superluminal drag of spacetime beyond the horizon. Even though these comparisons help, the true strangeness of the event horizon goes beyond everyday experience. It is not simply a dangerous region of intense gravity but a literal boundary to the observable universe. Nothing from beyond it can influence events outside, at least not in any classical sense. This has profound implications for physics. If information about matter disappears beyond the horizon, does it cease to exist? Or is it somehow preserved, hidden in ways we do not yet fully understand? These questions form the basis of deep paradoxes that stretch into the domains of quantum mechanics and thermodynamics. It is important to stress that the event horizon is not a physical surface where matter can crash or burn. There is no wall or membrane waiting for an object as it falls. Instead, it is a region defined purely by geometry. One moment an object is visible to the outside universe, the next it is not. This sudden disappearance is not because the object is destroyed at the boundary but because space-time itself bends so completely that all possible paths forward are inward paths. For the falling traveler, the crossing is uneventful, at least until tidal forces closer to the singularity begin to stretch matter in violent and unimaginable ways. Understanding the event horizon is also essential for interpreting astronomical data. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, what it revealed was not the horizon itself but the silhouette it casts against glowing material swirling outside. The horizon's presence is inferred by the absence it creates, a dark void surrounded by light. This observational breakthrough brought into sharp focus the idea that the horizon is not merely a theoretical boundary on paper but a real, observable phenomenon shaping the dynamics of galaxies. The event horizon, then, is both a practical concept in physics and a profound metaphor. It marks the border where our current knowledge meets its limits, where established laws give way to mysteries. To probe further into the behavior of matter and energy near this boundary, we must turn to the deeper physics of black holes themselves. The horizon is not the end of the story but the gateway to what lies within, and it is there, in the warped geometry and collapsing core, that some of the greatest questions of modern science await. The nature of space-time near a black hole defies ordinary intuition, forcing us to abandon the familiar rules of distance, duration, and motion that govern our everyday world. General relativity tells us that mass and energy warp space-time, curving it in a way that dictates how objects move. For ordinary stars or planets, this curvature is relatively gentle, like a shallow bowl guiding marbles to roll inward. But near a black hole, the curvature becomes so extreme that space-time itself funnels toward the singularity. Space and time no longer behave as distinct and steady backdrops. Instead, they twist, stretch, and ultimately exchange roles in ways that challenge even the imagination of physicists. To understand this curvature, it helps to imagine space-time as a flexible sheet. Place a small object on the sheet and it creates a minor dent, causing other marbles to roll toward it. Place a massive object like a star, and the dent deepens into a well, bending paths more dramatically. A black hole, however, does not merely create a deeper well, it creates a pit so steep that it becomes bottomless. The walls of this pit are the geometry of space-time itself, and once an object reaches the critical slope defined by the event horizon, it is carried inexorably downward. Unlike the sheet analogy, however, this is not a force pulling matter inward but the structure of reality itself guiding every possible trajectory toward the same fate. This profound bending of space-time has remarkable consequences for the flow of time. One of the predictions of general relativity is that clocks run more slowly in stronger gravitational fields. This effect, known as gravitational time dilation, is negligible near Earth but becomes dramatic around a black hole. For an observer hovering safely at a distance, time for a companion near the horizon seems to tick at a slower and slower rate. Light emitted from the falling companion becomes stretched to longer wavelengths, first turning red and then fading away entirely as the clock appears to freeze. From the distant perspective, it seems as though the traveler never truly crosses the horizon, but instead lingers there for eternity, gradually dissolving into darkness. The traveler, on the other hand, experiences nothing unusual at the horizon itself. Their own watch ticks normally, their heartbeat remains steady, and in their frame of reference they fall smoothly across the boundary. For them, the passage of time feels unbroken. In fact, their journey from the horizon to the singularity, depending on the size of the black hole, might be surprisingly brief. In a stellar mass black hole, the fall could last only seconds before tidal forces rip matter apart. In a supermassive black hole, by contrast, the journey might last hours before reaching the violent center. The dissonance between the external and internal perspectives is not a trick of perception but a fundamental feature of relativity, a reminder that time is not absolute but woven into the geometry of space-time itself. For an outside observer watching matter fall into a black hole, the picture is even stranger. Imagine a star wandering too close to the gravitational field and being torn apart, its gas spiraling in a luminous disk of glowing plasma. The material closest to the horizon whirls at nearly the speed of light, heated to millions of degrees and releasing radiation that can be seen across the universe. To a distant telescope, however, the final moments of the gas are never observed directly. The radiation grows dimmer and more redshifted, smeared into a faint afterglow that seems to hover forever just above the event horizon. From this vantage point, the black hole never quite consumes what it captures, it merely stores it in a vanishingly thin layer of frozen time. This illusion of permanence is one of the most compelling visual paradoxes in astrophysics. The consequences of space-time curvature extend beyond the horizon itself. Black holes are not isolated monsters hiding quietly in the void, they shape their environments dramatically. Matter falling toward them generates intense magnetic fields, creating jets that blast material outward at nearly light speed, sometimes stretching across thousands of light years. Thus, paradoxically, objects defined by their invisibility often announce their presence in the loudest ways possible, acting as cosmic engines that regulate galaxies and influence the evolution of stars around them. What remains hidden, however, is the fate of anything that crosses the horizon. For the outside universe, the horizon acts as a kind of one-way mirror, everything beyond it is sealed off. The falling traveler's time continues, but no message can escape to tell their story. The geometry ensures that all light cones, the possible paths through space-time, tilt inward, leaving no possibility of turning back. In this sense, the horizon is not just a boundary but a transformation of the very structure of reality. Space becomes time-like, forcing everything forward in the same direction, and time itself becomes bound to the inward plunge. The picture we gain from these considerations is a layered one. At the edges of a black hole, space-time curves so dramatically that it reshapes our concepts of space, motion, and time. To the distant eye, objects freeze and fade, suspended forever on the brink. To the infalling observer, the journey is swift and irreversible. Both accounts are true, though they cannot be reconciled within ordinary intuition. They are reconciled only by the mathematics of relativity, which tells us that the laws of physics permit multiple, equally valid perspectives depending on the observer's frame of reference. All of this leads naturally to deeper questions about what lies within. The curvature outside the horizon is extreme but still describable by the equations of general relativity. Inside, however, those equations point toward a singularity, a place where density becomes infinite and space-time collapses into something beyond our understanding. The event horizon, then, is not the end of the story but the doorway to a realm where physics itself may need to be rewritten. To move closer to that mystery, we must follow the path of theory into the singular heart of the black hole, where the known laws of nature break down and speculation takes over. At the center of every black hole, at least according to the equations of general relativity, lies the singularity. This word itself carries an aura of strangeness, and in physics it refers to a place where the normal rules break down, where the equations that normally describe the universe lose their power to make sense. The singularity is not a physical object in the usual sense. It is not a ball of matter or a knot of energy. It is a point, or, more accurately in rotating black holes, sometimes a ring, where density becomes infinite, volume shrinks to nothing, and space-time curvature diverges without bound. In theory, all the matter and energy that once composed a massive star, and whatever else falls into the black hole afterward, are compressed into this dimensionless location. To describe it in words feels impossible, because our language presumes dimensions, extension, and limits. The singularity is by definition the absence of all of those things. The most striking feature of the singularity is its prediction of infinite density. In ordinary physics, infinities are not accepted as real descriptions of nature but as signs that a theory has reached its limit. When Newton's laws could not handle the behavior of light or very fast-moving objects, they gave way to Einstein's relativity. When classical mechanics could not account for the atomic world, it was replaced by quantum mechanics. In each case, the infinity was not a real physical property but a clue that a deeper level of description was required. The singularity of a black hole therefore may not be a literal point of infinite density. Instead, it may be an indicator that general relativity, powerful as it is, cannot by itself describe conditions of such extreme gravity. A new theory, one uniting relativity with quantum mechanics, would be required to reveal what really happens at the core. Even without a complete theory, the implications of a singularity are profound. It represents not just a breakdown of physics but of predictability itself. In general relativity, the behavior of the universe is governed by deterministic equations. If you know the initial conditions, you can calculate what will happen in the future. Near the singularity, this determinism collapses. The curvature of space-time becomes infinite, and the equations can no longer tell us what happens next. This creates a kind of horizon not only in space but in knowledge. Just as the event horizon marks the limit of what we can see, the singularity marks the limit of what we can know, at least with our current tools. This has led to deep debates among physicists about whether singularities truly exist in nature or whether they are only mathematical artifacts. Roger Penrose and Stephen Hawking showed through their singularity theorems that under very general conditions, the collapse of matter inevitably leads to singularities. Their work suggested that singularities are not just peculiar solutions but unavoidable features of gravity pushed to its limits. At the same time, many believe that quantum effects, ignored in classical relativity, would soften the singularity or replace it with something more physically reasonable. Theories such as loop quantum gravity and string theory propose alternatives, where the core of the black hole might be a region of finite though extreme density, or perhaps even a gateway to another space-time region. Until a complete theory of quantum gravity is achieved, the singularity remains an unresolved puzzle. Beyond the scientific definitions lies a deeper philosophical dimension. The singularity confronts us with the limits of human comprehension. It is a place where not only our equations but our very concepts, space, time, matter, cause and effect, fail to apply. To contemplate it is to confront the possibility that reality itself contains regions forever beyond rational grasp. For some, this is unsettling, as it suggests an irreducible barrier to knowledge. For others, It is inspiring, a reminder that the universe is larger and stranger than our imagination can easily encompass. The singularity is the modern equivalent of the blank spaces on ancient maps. The places labeled here be dragons, warning that what lies beyond is unknown and perhaps unknowable. Philosophers have drawn parallels between the singularity and ancient notions of the absolute or the infinite. In theology, the infinite has often been associated with divinity, a realm beyond human categories. In mathematics, infinity is a symbol of both power and paradox, capable of producing contradictions if handled without care. The black hole singularity unites these threads, serving as a scientific embodiment of the infinite, a place where numbers and measurements dissolve into abstraction. Some have even argued that our fascination with black holes is rooted in their resonance with deep archetypes, the abyss, the void, the hidden center. The singularity also raises questions about the nature of reality itself. If all the matter of a star is compressed into an infinitely small point, what does that mean for the identity of matter? Does the concept of object or thing survive in such a state, or does the singularity erase individuality entirely? Furthermore, if information is carried into the singularity, is it annihilated, or does it persist in some form beyond our reach? These questions are not merely technical but philosophical, cutting to the heart of how we think about existence. In popular imagination, the singularity is often portrayed as a doorway, a passage to another universe or dimension. While such ideas are speculative, they capture something essential about the mystery. The singularity is not only a place of endings but potentially a place of beginnings. If our theories break down there, then so too might our assumptions about finality. The singularity could conceal the birth of new structures, new spaces, even new universes, hidden beyond the reach of our current science. Whether it is a true physical reality, a mathematical artifact, or a gateway to something beyond, the singularity stands as the core of the mystery of black holes. It is the point toward which all paths inside the horizon converge, the center around which both science and imagination revolve. To pursue an understanding of it is to acknowledge both the power of human reason and its limits, to stretch our concepts to their breaking point and beyond. And though the singularity resists definition, it also invites us to search for the theory that will one day replace the infinity with something comprehensible, transforming mystery into knowledge while preserving the sense of wonder that first drew us to the question of what lies inside a black hole. When matter falls into a black hole, it seems at first that its fate is clear. The material crosses the event horizon, is cut off from the outside universe, and eventually joins whatever strange state lies at the singularity. From the perspective of classical general relativity, nothing more needs to be said. The black hole grows in mass, and the outside world simply loses access to whatever information the matter once carried. Yet physics has long relied on the principle that information cannot be destroyed. Even if matter changes form, its underlying physical information, the arrangement of particles, their quantum states, the structure they once held, must persist in some way. A burned book is no longer readable, but in principle, every bit of information about the ink and paper survives in the smoke and ash. Black holes appear to defy this rule. Once something crosses the horizon, its information seems to vanish forever. This tension came to a head in the 1970s, when Stephen Hawking applied quantum field theory to the curved space-time around a black hole. To his surprise, he found that black holes are not entirely black. They emit radiation, now known as Hawking radiation, due to quantum fluctuations near the horizon. Pairs of virtual particles constantly flicker into existence in empty space, one positive and one negative, usually annihilating each other almost instantly. Near the horizon, however, one particle can fall in while the other escapes, making the black hole slowly radiate energy. This process means that black holes are not eternal, they gradually lose mass and, over immense timescales, eventually evaporate away completely. At first, this seemed like an elegant resolution. Black holes were no longer perfect prisons, they had a way to release energy back into the universe. But Hawking's calculation showed that the radiation is purely thermal, like heat from a fire, containing no information about what fell into the hole. If the black hole eventually disappears entirely, all that remains is a bath of random radiation, devoid of the structured information that once described stars, planets, or perhaps even human beings. This result clashed violently with one of the most basic principles of quantum mechanics, unitarity, the idea that information is never lost but always encoded in the evolution of the wave function. The conflict between relativity and quantum mechanics at the heart of this paradox shook theoretical physics, and it became known simply as the black hole information paradox. Hawking himself initially argued that information truly is destroyed in black holes, forcing a revision of the laws of physics. This suggestion was deeply unsettling to many, since it would undermine the consistency of quantum mechanics. Over the decades, the paradox spurred a multitude of attempts to reconcile the two great theories. Gradually, the consensus shifted toward the view that information must in fact be preserved, but the mechanism by which this happens remains elusive. One of the most influential proposals is the holographic principle. Inspired by work in string theory and in particular by Gerard T. Hooft and Leonard Susskind, this idea suggests that all the information about matter that falls into a black hole is not lost but is encoded on its surface, the event horizon itself. Just as a two-dimensional hologram encodes a three-dimensional image, the surface of the black hole might encode everything about its interior. This principle received powerful mathematical support in the 1990s with the development of the ADS-CFT correspondence, a conjecture by Juan Maldacena that relates a theory of gravity in a curved space to a lower dimensional quantum field theory without gravity. In this picture, the information paradox is resolved because the black hole's evaporation process is secretly unitary, with information stored and eventually released in correlations within the radiation. Another, more controversial idea is the firewall hypothesis. Proposed in the early 2010s, it argues that the event horizon may not be the smooth, uneventful boundary predicted by relativity but instead a searing wall of energy that burns up anything falling in. According to this view, the entanglement of particles across the horizon required for Hawking radiation to remain consistent would eventually break down, releasing energy in a violent barrier. This would solve the paradox by allowing information to be radiated outward more directly, but it comes at the cost of destroying one of relativity's central insights, that crossing the horizon should feel locally unremarkable. The firewall idea remains highly debated, as it forces a choice between deeply held principles in physics, either the smoothness of space-time at the horizon or the preservation of information. String theory has also offered possibilities. In this framework, the microstates of a black hole, the fundamental ways it can exist, are not hidden at a singularity but spread across extended structures described by strings and brands. Calculations in certain kinds of string theory have shown that the entropy of black holes, a measure of the number of microscopic configurations consistent with their overall properties, can be explained by counting these microstates. This suggests that information is not lost but is encoded in the detailed quantum structure of the black hole itself. When it evaporates, the information would leak out subtly encoded in the radiation, though in ways too complex to be seen in Hawking's original calculation. Despite decades of work, no single resolution has achieved universal acceptance. The information paradox continues to be a guiding problem in the search for a theory of quantum gravity. Its significance goes beyond black holes themselves, because it represents a clash between two pillars of modern physics. Relativity provides a geometric description of space-time and gravity, while quantum mechanics describes matter and energy at the smallest scales. Each is extraordinarily successful in its own domain, yet when pushed together at the edge of a black hole, they appear to contradict each other. The paradox is therefore not only about black holes but about the consistency of physics itself. The persistence of the paradox has had an unexpected benefit. It has stimulated some of the most creative developments in theoretical physics. Ideas such as holography, quantum entanglement as a building block of space-time, and the possibility that our universe itself may be a holographic projection, all trace their roots in part to attempts to solve the black hole puzzle. What began as a seeming contradiction in Hawking's calculation has blossomed into a rich field of inquiry, reshaping our understanding of space, time, and information. As things stand today, the majority of physicists believe that information is not lost in black holes, though the exact mechanism by which it is preserved remains uncertain. Hawking himself eventually conceded this point late in his career, acknowledging that quantum theory's demand for unitarity was likely correct. Yet the paradox remains unresolved, serving as a reminder that even the most advanced theories have limits, and that black holes, far from being mere astrophysical curiosities, are laboratories for the deepest questions about reality. They remind us that the act of falling into darkness is not only a physical journey but also a conceptual one, carrying us to the boundaries of what we know and into the territory of what we do not yet understand. In the mid-1970s, Stephen Hawking made a discovery that forever changed how scientists think about black holes. Until then, black holes were believed to be absolute traps. Nothing could escape them, not matter, not light, not information. They were perfect sinks in the fabric of space-time, growing larger whenever they consumed anything but never giving anything back. The idea seemed final and absolute, but Hawking's insight showed that even the most impenetrable structures in the universe are subject to the restless fluctuations of quantum mechanics. The result of his calculations was startling: black holes are not perfectly black at all. Instead, they emit a faint stream of radiation, now called Hawking radiation, which slowly drains them of their mass and energy. The origin of this radiation lies in the peculiar nature of the quantum vacuum. What we usually think of as empty space is, according to quantum theory, never truly empty. It is a seething arena where particle-antiparticle pairs are constantly appearing and disappearing. These virtual particles exist for the briefest instants, borrowing energy from the vacuum and then annihilating each other, returning their energy to the void. In ordinary conditions, this constant dance remains invisible, its effects detectable only in subtle ways. Near the event horizon of a black hole, however, the story changes. There, the gravitational field is so intense that when such a pair forms, one particle may fall into the black hole while the other escapes. The result is a real particle streaming away into space, while its partner is trapped inside. To an outside observer, it appears as if the black hole itself is radiating. From the black hole's perspective, the particle that falls in carries negative energy relative to the outside universe. When this happens, the mass of the black hole decreases. Over time, as more and more pairs are split apart by the horizon, the black hole steadily loses mass and energy, emitting radiation that is almost perfectly thermal. This slow leakage of energy implies something extraordinary: black holes can evaporate. For a large black hole, such as those formed by collapsing stars, the process is unimaginably slow, lasting far longer than the current age of the universe. But for very small black holes, if they exist, evaporation could occur on much shorter timescales, potentially ending in a final burst of radiation as the black hole disappears entirely. This evaporation process turned the once eternal image of black holes upside down. They are no longer permanent scars on the fabric of the cosmos but temporary features, destined eventually to vanish. The implications ripple outward into nearly every area of physics. Black holes had been seen as the ultimate destroyers of information, places where anything could fall and be erased from the universe. Hawking's discovery complicated this picture. On the one hand, evaporation provides a way for black holes to give something back, releasing energy into space. On the other hand, the radiation itself carries no obvious information about the matter that originally fell in. It is like the glow of a hot coal, revealing only the temperature and size of the object but not the details of its composition. This is where Hawking radiation connects directly to the information paradox. If a black hole evaporates completely, and the radiation it emits is purely thermal, then everything that ever fell inside is gone without a trace. The structure of atoms, the arrangement of molecules, the imprint of any signal or pattern, none of it seems to survive. This apparent destruction of information is at odds with quantum mechanics, which demands that information be conserved. In quantum theory, processes may scramble information beyond recognition, but they never annihilate it. Hawking's calculation suggested otherwise, and this tension gave rise to one of the deepest puzzles in modern science. Over the decades, physicists have examined Hawking radiation from many angles, trying to uncover hidden patterns in it that might encode the lost information. Some suggest that the radiation is not perfectly random but subtly correlated, carrying away information in ways too fine-grained for Hawking's original analysis to capture. Others point to the holographic principle, which proposes that all the information that falls into a black hole is somehow stored on its surface area rather than lost to the singularity, and that this information might be gradually released through the evaporation process. In this view, the black hole acts less like an eraser and more like a highly compressed hard drive, with the data leaking out over time. The idea that black holes emit radiation also has profound consequences for cosmology. In the early universe, conditions may have allowed for the formation of tiny primordial black holes, much smaller than those produced by stellar collapse. If they formed, many of them would have long since evaporated, but their final explosions might leave detectable signatures, from bursts of high-energy particles to subtle effects in the cosmic background radiation. The search for such signals continues, as they could provide not only evidence for Hawking radiation but also insights into the conditions of the infant cosmos. Despite the elegance of Hawking's theory, it remains challenging to test directly. For stellar mass and supermassive black holes, the radiation is so faint that it is overwhelmed by other astrophysical processes. The temperature of the radiation is inversely proportional to the mass of the black hole, which means that the bigger the black hole, the colder it is. A black hole with the mass of the Sun would radiate at a temperature of only a few nanokelvins, far colder than the cosmic microwave background. Such radiation is effectively undetectable with current technology. This limitation makes the search for indirect signatures, such as those from primordial black holes, all the more important. Still, even without experimental confirmation, Hawking radiation is widely accepted because it arises from combining well-established principles of quantum mechanics with relativity. Its existence is one of the clearest signs that gravity and quantum physics cannot remain separate forever. To fully understand the evaporation process, and to resolve the information paradox it creates, a complete theory of quantum gravity is needed. Such a theory would not only clarify the fate of information in black holes but also illuminate the fundamental structure of space-time itself. In the end, Hawking radiation has reshaped black holes from being one-way prisons to being dynamic, evolving systems. It has revealed them as temporary features of the cosmos, slowly leaking their secrets back into space. Yet it has also deepened the mystery, because the form in which those secrets emerge, whether as scrambled patterns in the radiation or as hidden correlations we have not yet deciphered, remains uncertain. The radiation is both a beacon and a riddle, a signal from the edge of physics pointing toward a deeper theory still waiting to be discovered. Black holes, once thought to be silent, are in fact whispering to the universe, though we are still struggling to understand the language in which they speak. When considering the internal structure of a black hole, one immediately confronts the limits of human knowledge. General relativity provides a picture that is at once stark and troubling. According to Einstein's equations, Once matter crosses the event horizon, it is inexorably drawn inward to a single point, the singularity, where density becomes infinite and space-time curvature diverges without bound. This classical model of the singularity has long stood as the standard description, but it is also the clearest signal that general relativity cannot be the final word. Infinity is rarely a feature of nature itself, but more often a sign that the theory being used has been stretched beyond its domain of validity. The singularity represents not so much a physical object as a breakdown in our equations, a place where our current understanding of space, time, and matter ceases to function. In the classical model, the singularity sits at the very core of the black hole, hidden from outside view by the event horizon. All matter and energy that falls into the black hole adds to its mass, which in turn shapes the space-time curvature that guides further infall. The mathematics is clear, but the physical meaning is murky. What does it mean for matter to be crushed to an infinitesimal point? Can there be a physical state of infinite density? Most physicists suspect that this is not the final description but rather an indicator that new physics, likely quantum in nature, is required. Quantum mechanics has always imposed limits on compression and uncertainty, and many expect that a proper quantum theory of gravity would resolve the singularity into something finite, though radically different from ordinary matter. One possibility often discussed is the idea of black hole remnants. In this scenario, evaporation through Hawking radiation does not reduce the black hole to nothing but instead halts at a finite size, leaving behind a stable relic. Such remnants would contain the information of everything that fell into the black hole, stored in some as yet unknown form. This would resolve the information paradox neatly, since the data would never be lost, only hidden. However, this idea raises its own difficulties. If every black hole that ever formed leaves behind an indestructible remnant, the universe could be filled with countless such objects, each carrying vast amounts of information. The implications for cosmology and particle physics are immense, and the lack of observational evidence for such remnants has left the idea controversial. Another alternative involves wormholes, hypothetical tunnels in space-time that could connect the interior of a black hole to another region of the universe, or perhaps to an entirely different universe. In certain speculative models, matter that falls into a black hole does not collapse into a singularity but instead travels through a throat to emerge elsewhere. These ideas have captured the imagination of both physicists and science fiction writers, though they remain highly theoretical. Wormholes that could actually be traversed by matter would require exotic forms of energy to remain stable, and no evidence for such energy exists. Nevertheless, the mathematics of general relativity does permit such solutions, and they remain on the list of possible alternatives to the classical singularity. A more conservative but still radical possibility is that the interior of a black hole contains a quantum core rather than a singularity. In this view, the collapse of matter is halted not at zero size but at some finite, extremely dense state governed by quantum gravitational effects. This core could be thought of as a new phase of matter or space-time itself, something fundamentally different from anything observed in laboratories. Theories of loop quantum gravity, for example, suggest that space-time has a discrete structure at the smallest scales, preventing infinite compression. In such models, the singularity is replaced by a finite, though extreme, region that might even bounce, leading to the possibility of black holes being connected to new expanding universes on the other side. The speculation about internal structures is not purely academic. Each hypothesis has consequences for how black holes interact with their environment and how they might be observed. If remnants exist, they could alter the expected signatures of black hole evaporation. If wormholes are real, they could have implications for cosmic connectivity and the ultimate fate of information. If quantum cores replace singularities, they would point the way toward a deeper theory of gravity, perhaps reconciling general relativity with quantum mechanics. The challenge is that none of these possibilities can yet be directly tested. The event horizon hides the interior from observation, and no signal can escape from within to carry news of what lies there. Nevertheless, indirect approaches remain possible. For instance, the detailed properties of Hawking radiation might carry subtle fingerprints of the internal structure. The gravitational waves emitted when black holes merge could, in principle, reveal whether their interiors behave exactly as classical general relativity predicts or whether there are deviations that hint at new physics. Advanced observatories may one day gather enough data to test these ideas, though for now they remain in the realm of theoretical exploration. The study of black holes often feels like standing at the edge of a vast ocean of ignorance, where every attempt to peer deeper leads to more profound questions. The classical singularity model is both compelling and unsatisfactory, a signpost pointing beyond our current understanding. The alternatives, whether remnants, wormholes, or quantum cores, offer glimpses of possible resolutions but also introduce new mysteries. Each suggests that black holes are not merely destructive objects but also keys to the most fundamental structure of reality. They are where the known laws of physics break down, forcing us to imagine what might replace them. In the end, the true internal structure of black holes remains hidden, not only behind the veil of the event horizon but also behind the veil of incomplete theory. What lies inside may be stranger than any of our current hypotheses, something that challenges not just the equations of relativity and quantum mechanics but our very notions of space and time. Until a complete theory of quantum gravity is achieved, and perhaps until new observational breakthroughs are made, the interior of black holes will remain one of the deepest enigmas of the cosmos, a mystery waiting for the next great leap in human understanding. The idea of wormholes, or Einstein-Rosen bridges as they are sometimes called, emerges directly from the equations of general relativity. In 1935, Albert Einstein and Nathan Rosen proposed a solution that suggested space-time might contain bridges connecting distant regions, like tunnels piercing through the cosmic fabric. In theory, such structures could provide shortcuts between different locations in the universe, or even link entirely separate universes. The mathematical formalism gave rise to one of the most intriguing possibilities in physics, one that has inspired scientific speculation and artistic imagination alike. Yet the path from elegant equations to physical reality is fraught with difficulty, for wormholes, while mathematically consistent, are unstable in most formulations and collapse too quickly to be traversed by matter. The Einstein-Rosen bridge, in its original form, can be thought of as a model for the geometry of a black hole. According to this solution, what looks like a singularity hidden behind an event horizon may instead be a connection to another space-time region. The interior of a black hole could, in principle, lead somewhere else, perhaps to another black hole in a different universe. This suggestion fueled early dreams of cosmic passageways, but closer analysis revealed that such bridges would pinch off before anything could cross them. An observer falling into the black hole would still encounter a singularity and would not survive to emerge elsewhere. Thus, the Einstein-Rosen bridge remained more of a theoretical curiosity than a physical mechanism for travel. Later developments introduced the idea of traversable wormholes, structures that could remain open long enough for matter, or even people, to pass through. For such wormholes to exist, however, something extraordinary is required: exotic matter with negative energy density, capable of counteracting the natural tendency of space-time to collapse the tunnel. Quantum field theory allows for the existence of negative energy in certain contexts, such as the Casimir effect, but whether enough of it could be harnessed to stabilize a wormhole remains speculative. Without this exotic ingredient, wormholes cannot be traversed. With it, they could, at least in principle, serve as cosmic gateways. The question then arises, could one pass beyond the event horizon of a black hole and find oneself in another universe? In classical general relativity, the answer is grim, for the singularity stands as a barrier that no traveler can survive. But in speculative models involving wormholes, the event horizon could be reimagined as an entrance rather than a prison. To step across the horizon might be to enter the throat of a wormhole, with the possibility of emerging elsewhere. Yet such models face the challenge of consistency. Traversable wormholes raise paradoxes, particularly involving causality. If one could journey through a wormhole faster than light would take to cross normal space, time travel might become possible, leading to closed time-like curves and all the paradoxes they entail. Physics tends to resist such violations of causality, and many believe that deeper principles would prevent wormholes from functioning in this way. Despite these barriers, the concept of wormholes has captured the collective imagination. In science fiction, wormholes are often portrayed as portals across galaxies, devices that make interstellar travel feasible within human timescales. From television series to novels to films, they serve as narrative devices that shrink the otherwise unimaginable distances of space into something manageable for storytelling. Sometimes these depictions are rooted in real physics, drawing on the notion of space-time curvature and the energy requirements of traversable tunnels. Other times they are pure fantasy, symbols of humanity's longing to escape confinement and explore the unknown. In scientific circles, wormholes have been more than just curiosities. They have served as laboratories for thought experiments about quantum gravity, information, and the structure of space-time. Theoretical physicists have used them to probe questions about entanglement and causality, leading to provocative ideas such as the ER equals EPR conjecture, which suggests a deep connection between wormholes and quantum entanglement. According to this idea, pairs of entangled particles might be linked by microscopic wormholes, offering a unifying perspective on two seemingly different phenomena. While still speculative, this line of thought illustrates how wormholes continue to stimulate new ways of thinking about the foundations of physics. Artistic interpretations often go beyond strict science but resonate with the philosophical implications. A wormhole can symbolize escape from the inescapable, a hidden path where none seems possible, or a bridge between life and death, reality and dream. The metaphorical power of the wormhole is immense, allowing it to stand for transformation, transcendence, or the pursuit of knowledge. In visual art, wormholes are often depicted as swirling tunnels of light, gateways that beckon the viewer into other realms. In literature, they embody the tension between confinement and freedom, the struggle against the ultimate barriers of existence. Scientific exploration of wormholes is not without practical motivation. Even though they remain hypothetical, their study has pushed forward understanding of what relativity permits and how it interacts with quantum fields. By working through the conditions required for stability, physicists have gained insights into energy conditions in space-time, the limits of negative energy, and the constraints that any future theory of quantum gravity must respect. Thus, even if wormholes are never found in nature, they serve as valuable tools for probing the extremes of theory. In the end, wormholes straddle the line between the real and the imaginary. They emerge naturally from Einstein's mathematics, yet their physical existence remains unproven. They cannot be dismissed outright, for the history of physics is full of once speculative concepts that later found confirmation. At the same time, their most dramatic promises, instant travel across the cosmos or entry into other universes, remain tantalizing visions rather than realities. Whether they prove to be genuine features of the cosmos or enduring symbols of human curiosity, wormholes remind us of the richness of the universe and of our imagination. They show that even within the rigor of science, there is space for wonder, for daring to ask what lies on the other side of the impossible. When we attempt to peer into the heart of a black hole, we confront not only the mystery of the event horizon but the very limits of the theories that define modern physics. General relativity, with its geometric elegance, describes gravity as the curvature of space-time, and it works remarkably well on cosmic scales, predicting the existence of black holes with astonishing precision. Quantum mechanics, on the other hand, governs the microscopic realm, dictating the strange behaviors of particles and fields. Each framework is powerful in its own domain, but the interior of a black hole demands both simultaneously. Within the event horizon, densities and curvatures become so extreme that classical relativity collapses into singularities, while quantum mechanics lacks a mechanism to handle spacetime itself. It is here, in the very heart of the black hole, that the need for quantum gravity becomes inescapable. Without such a theory, we are left with contradictions, infinities, and unanswered questions. The failure of current physics arises from the incompatibility of its two central pillars. General relativity treats spacetime as smooth and continuous, capable of being curved but not quantized. Quantum theory insists that reality at the smallest scales is discrete, uncertain, and governed by probabilistic laws. When these two perspectives are forced together, as in the environment of a black hole singularity, the mathematics produces nonsensical results. Infinite densities, infinite curvatures, and the apparent destruction of information are not likely to be features of nature but indicators that our theories are incomplete. To understand what lies beyond the event horizon, we need a framework that can reconcile the smooth geometry of relativity with the granular dynamics of quantum fields. One of the approaches to this problem is loop quantum gravity. Instead of assuming that spacetime is a continuous fabric, this theory suggests that it has an atomic-like structure composed of finite loops woven together. These loops are unimaginably small, far below the scale of subatomic particles, but they provide a foundation in which spacetime itself is quantized. In such a framework, singularities can be avoided. The collapse of matter inside a black hole would not compress spacetime to a point of infinite density but to a finite, though extremely dense, quantum state. Some models derived from loop quantum gravity even propose that black holes may lead to bounces, where the interior does not end in a singularity but transitions into a new expanding region of spacetime, perhaps resembling another universe. The mathematics is still under development, and observational evidence is lacking, but this theory represents one path toward resolving the contradictions at the heart of black hole physics. Another contender is string theory, which posits that the fundamental building blocks of the universe are not point particles but tiny vibrating strings. Different modes of vibration give rise to different particles, unifying matter and forces under one framework. In string theory, black holes acquire new layers of structure. Rather than being empty regions surrounding a singularity, they can be described as complex states of strings and higher dimensional objects called brands. This description has allowed string theorists to calculate the entropy of black holes, matching the famous Bekenstein-Hawking formula that relates entropy to the area of the event horizon. By doing so, string theory offers a way to preserve information, showing that the apparent loss may be an illusion caused by using an incomplete theory. In this sense, black holes are not cosmic graves for information but intricate configurations of quantum states encoded in ways we do not yet fully understand. From string theory also arises the holographic principle, one of the most profound ideas in modern physics. According to this principle, all the information contained within a volume of space can be described by data inscribed on its boundary. In the context of black holes, this means that the three-dimensional interior might be fully represented by a two-dimensional surface, the event horizon itself. Information about everything that falls into a black hole would then be stored not inside the singularity but on the horizon, encoded like pixels on a cosmic screen. This radically changes the way we think about space, time, and reality itself, suggesting that our universe could, in some sense, be a holographic projection of deeper structures. The holographic principle provides a potential solution to the information paradox and hints at a framework in which gravity emerges from more fundamental quantum interactions. These approaches, whether loop quantum gravity, string theory, or the holographic principle, do not yet form a complete theory. They are steps toward reconciling the contradictions, each illuminating different facets of the mystery. Loop quantum gravity suggests a granular spacetime that avoids infinities. String theory provides a unified language for matter and forces, embedding black holes into a richer quantum framework. The holographic principle redefines the very meaning of space and interiority, suggesting that what lies inside may be nothing more than a projection of boundary information. Each points toward the same conclusion: our current theories are shadows of something deeper, and only by moving beyond them can we hope to describe the true nature of horizons. The pursuit of quantum gravity is not only about black holes. It touches the Big Bang, where similar singularities appear in cosmology, and it underpins the effort to understand the fabric of the universe at the most fundamental level. Yet black holes serve as the crucible for these questions, the cosmic laboratories where theory is pushed to its limits. Observations of gravitational waves, the shadow of the black hole image by the Event Horizon Telescope, and potential future detections of Hawking radiation may provide the clues needed to test these theories. For now, the horizon remains both a boundary of space and a boundary of knowledge, marking where relativity yields to quantum speculation. As we contemplate these possibilities, it becomes clear that the event horizon is not just a physical threshold but a conceptual one. To cross it in theory is to enter a domain where spacetime itself is no longer the smooth continuum of Einstein nor the probabilistic field of standard quantum mechanics. It is to enter a realm defined by a theory we have yet to write, where the geometry of reality is quantized and information is preserved in ways that challenge our intuition. The horizon, in this sense, is a frontier not only for matter and light but for human understanding. What lies beyond it will only be revealed when the quest for quantum gravity reaches its conclusion, unifying the deepest truths of the cosmos into a single, coherent vision. From a cosmological perspective, black holes are not only exotic objects hidden away in the depths of space but also fundamental players in the grand narrative of cosmic evolution. They are woven into the history of galaxies, stars, and the structure of the universe itself, influencing processes on scales far larger than their compact dimensions would suggest. Though they are defined by regions from which nothing can escape, their gravitational pull and energetic interactions shape their surroundings in ways that make them central to the life cycles of cosmic structures. To understand the evolution of the universe is therefore to understand the role of black holes, particularly the supermassive ones that lurk at the centers of galaxies. The early universe was a chaotic environment of rapidly forming stars, turbulent gas clouds, and emerging structures. Within this environment, the seeds of black holes were planted. Some formed from the collapse of the first massive stars, while others may have arisen from direct collapse of primordial gas clouds, skipping the stellar stage altogether. These black holes provided gravitational anchors in young galaxies, serving as gathering points for matter. Over cosmic time, they grew through accretion, feeding on the gas and dust around them, and through mergers, when galaxies collided and their central black holes eventually coalesced. Thus, from humble beginnings, the universe nurtured the giants we observe today, supermassive black holes containing millions or even billions of times the mass of the Sun. The growth of these supermassive black holes is not a passive process. As matter spirals inward, it forms accretion disks that heat up to extreme temperatures, emitting radiation across the spectrum and sometimes generating powerful jets that blast out into intergalactic space. These active galactic nuclei, or quasars in their most luminous form, can outshine entire galaxies. The energy they release is not confined to their immediate vicinity but can have profound consequences for the evolution of galaxies themselves. Radiation and jets from accreting black holes can heat and expel gas, regulating star formation within the host galaxy. In this way, black holes act as both creators and regulators, simultaneously driving growth and imposing limits. Observations show that the mass of a galaxy's central black hole is tightly correlated with the properties of the galaxy's bulge, such as its stellar velocity dispersion. This suggests a deep co-evolutionary relationship between galaxies and their central black holes. The mechanisms of feedback, radiation, winds, and jets appear to tie together the fates of these very different scales, from the tiny region around a black hole's event horizon to the vast expanses of a galactic disk. Without black holes shaping their growth, galaxies as we know them would likely be very different, and the structure of the cosmos would not have unfolded in the same way. On larger scales, mergers between galaxies play a central role in cosmic history, and black holes are at the heart of these dramatic encounters. When galaxies collide, their stars mostly pass by one another due to the vast distances between them, but their gas clouds and dark matter halos interact, leading to bursts of star formation and eventually to the sinking of their central black holes toward a common center. Over millions of years, the black holes spiral together, emitting gravitational waves as they close the gap, until they finally merge in a cataclysmic event. Such mergers not only produce some of the strongest gravitational wave signals in the universe but also give rise to even larger black holes, which then continue the cycle of accretion and feedback. This hierarchical process helps explain the enormous masses of black holes at the hearts of modern galaxies, including those observed in the most distant reaches of the universe. The link between black holes and galaxy formation is not merely observational but also theoretical. Cosmological simulations that attempt to reproduce the large-scale structure of the universe consistently find that including the effects of black hole feedback is necessary to match reality. Without it, galaxies in simulations grow too massive and form stars too quickly, leading to discrepancies with what telescopes actually observe. With black holes injecting energy back into their surroundings, simulations produce galaxies with properties much closer to those we see. This makes black holes indispensable in our understanding of how the luminous structure of the universe came to be. Supermassive black holes also illuminate the distant universe, serving as beacons that allow us to peer into cosmic history. Quasars powered by accretion onto black holes are visible across billions of light-years, revealing conditions in the universe less than 1 billion years after the Big Bang. Their presence at such early times raises questions about how black holes grew so quickly, suggesting that direct collapse black holes or other exotic processes may have seeded them. In this way, black holes not only shape cosmic structures but also serve as probes of epochs otherwise inaccessible to observation. The cosmological role of black holes extends further still. In theories of structure formation, they may help explain how matter assembled into the web of filaments and clusters that characterize the large-scale universe. Their mergers and growth contribute to the gravitational wave background that permeates space, offering a new channel of information about cosmic evolution. Some speculative ideas even suggest that black holes might act as seeds for entire new universes, linking them not just to galaxy formation but to the very possibility of cosmic rebirths. Thus, from the earliest epochs to the present, black holes stand as both destroyers and creators, consuming matter while shaping galaxies, regulating star formation, and radiating energy across space. Their story is inseparable from the story of the cosmos. To view the universe without them would be to imagine a completely different history, one in which galaxies lack their central anchors, in which cosmic feedback is absent, and in which the luminous structure of space unfolds along alien lines. As we deepen our observations, from gravitational waves to high-resolution imaging of galactic centers, we continue to uncover the centrality of black holes in the grand tapestry of the universe. They are no longer merely enigmatic points of darkness but central engines of cosmic evolution, guiding the universe's growth across billions of years. In the past decade, black holes have shifted from the realm of abstract theoretical constructs into tangible objects that we can, in some sense, see and measure. This transformation has been driven by a series of extraordinary observational breakthroughs that have turned speculation into direct evidence. Among these, two stand out above all: the imaging of a black hole's shadow by the Event Horizon Telescope and the detection of gravitational waves by LIGO and its partner observatories. These achievements have opened a new era in astrophysics, where black holes are no longer silent enigmas but active subjects of detailed investigation. They represent not only technical triumphs but also profound shifts in how humanity experiences and understands the universe. The Event Horizon Telescope, or EHT, is not a single instrument but a global network of radio observatories operating together in a technique known as very long baseline interferometry. By synchronizing telescopes scattered across the Earth, from the deserts of Chile to the mountains of Hawaii and even the frozen plateau of Antarctica, the EHT achieves a resolving power equivalent to a telescope the size of the entire planet. This unprecedented collaboration made it possible to target the most extreme objects in the universe, the supermassive black holes at the centers of galaxies. After years of coordination, data collection, and analysis, the EHT released its first historic image in 2019, the shadow of the black hole at the core of the galaxy M87. The image was more than a technical marvel. It was a confirmation of Einstein's general relativity under the most extreme conditions imaginable. The glowing ring surrounding the dark shadow was not a direct picture of the black hole itself, since the interior remains invisible, but rather the light bent and warped by gravity as matter swirled around the event horizon. The shadow's shape and size matched predictions from relativity with astonishing precision, offering one of the most direct proofs yet that black holes exist as the theory describes them. What had long been imagined through mathematics and simulations was now visible to human eyes, a photograph of the edge of space-time. Following the M87 image, the EHT collaboration continued its work and in 2022 released the image of Sagittarius A*, the supermassive black hole at the heart of our own Milky Way. This achievement was even more challenging, as Sagittarius A* is smaller and changes on timescales of minutes, whereas M87's vast black hole evolves more slowly. The successful imaging of our galactic center demonstrated the power of the technique and provided another opportunity to test relativity and black hole physics. Together, these images stand as milestones in observational astronomy, the first glimpses into realms that had previously been thought unseeable. At the same time that astronomers were assembling the planet-wide camera to photograph black holes, another revolution was underway. In 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, announced the first detection of gravitational waves. These ripples in space-time, predicted by Einstein a century earlier, were produced by the merger of two black holes more than 1 billion light-years away. The signal was faint, a tiny stretching and squeezing of space measured as distortion smaller than the width of a proton, but it carried with it an extraordinary story. It was the direct evidence of black holes colliding, spiraling together in their final death dance, and merging into a larger singularity. For the first time, astronomers had heard the universe in gravitational waves, a new sense to complement sight. Since that first detection, LIGO, along with its European counterpart Virgo and later the Japanese Kagra Observatory, has recorded dozens of events, many involving black holes. These signals have allowed scientists to reconstruct the masses, spins, and dynamics of black holes across the universe. Each detection adds to the catalogue, painting a picture of populations of black holes that differ from what had been expected, including surprisingly massive ones formed from stars and perhaps even primordial ones born in the earliest epochs of the universe. Gravitational wave astronomy is now a field in its own right, providing data about black holes that no electromagnetic observation could reveal. The significance of these breakthroughs goes beyond their immediate scientific results. They represent a new way of knowing the cosmos. The EHT gave us vision of the invisible, while LIGO gave us hearing of the inaudible. Together they expand the human sensory experience, turning the abstract equations of relativity into experiences that can be recorded and shared. They also demonstrate the power of global collaboration, as both the EHT and gravitational wave detectors depend on networks of scientists, institutions, and nations working together toward a shared goal. Black holes, once thought of as inaccessible, have become laboratories for testing the very foundations of physics. These achievements also sharpen our questions. The shadow of a black hole confirms relativity's predictions, but does it leave room for new physics hidden in the fine details? Gravitational waves reveal the violence of mergers, but do they carry subtle signatures that point to quantum gravity effects or deviations from general relativity? The current generation of instruments may not yet have the precision to answer these questions, but their successors, already being designed, aim to push the boundaries further. Space-based observatories such as the planned LISA mission will extend gravitational wave astronomy to new frequencies, sensitive to mergers of supermassive black holes at the hearts of galaxies. Future expansions of the EHT may yield sharper images, perhaps even movies of black hole dynamics, revealing how matter flows and jets are launched in real time. For the public, the impact of these breakthroughs has been profound. The image of the M87 black hole became an icon overnight, a symbol of humanity's ability to reach beyond imagination into direct perception of the universe's most extreme phenomena. Gravitational wave detections are less visually striking but equally transformative, offering the thrill of hearing cosmic events across unimaginable distances. These achievements remind us that science is not only about equations and theories but about experiences, moments where human knowledge takes a leap into the unknown and emerges with something tangible. The observational breakthroughs of the past decade have brought us closer to the horizons that once seemed forever beyond reach. They have confirmed relativity, revealed populations of black holes, and demonstrated the reality of phenomena once thought forever hidden. At the same time, they have opened doors to deeper mysteries, urging us to refine our theories, expand our instruments, and continue the quest to understand what lies beyond the shadows. In the glow of an accretion disk and the vibrations of space-time itself, we find not the end of the story but the beginning of a new chapter, one where black holes are no longer invisible enigmas but luminous guides to the deeper truths of the cosmos. From the moment the concept of black holes entered scientific discourse, it began to seep into philosophy, literature, and art, becoming more than a physical idea and transforming into a cultural symbol. Black holes are unique in that they are not merely astrophysical entities but also metaphors for mystery, for the limits of knowledge, and for the encounter between the known and the unknowable. They mark a frontier where science pushes against its own boundaries, and that very boundary has always fascinated the human imagination. Over the decades, the image of black holes has expanded far beyond the laboratories and observatories into the realms of thought, creativity, and collective cultural meaning. Philosophically, black holes embody the ultimate test of human reason. They are not directly observable in the conventional sense. Their very definition is that they conceal information behind an event horizon. In this way, they represent a paradoxical intersection of presence and absence, being and nothingness. Existential philosophers have drawn on this imagery to reflect on the nature of human limitation. To speak of falling into a black hole is not only a description of physical descent into extreme gravity but also a metaphor for confronting situations where comprehension collapses, where categories of thought break down. The singularity, in particular, is an evocative symbol of the limits of rational inquiry, a place where laws fail and where reason itself is swallowed. Art and literature have embraced this symbolism with enthusiasm. Black holes appear in novels, paintings, and films as emblems of both terror and wonder. They embody the sublime in the classical sense, that mixture of awe and fear experienced in the face of something vast, incomprehensible, and overwhelming. The cinematic portrayal of black holes, from science fiction epics to contemplative dramas, often leans into this duality. On the one hand, the black hole is a devouring monster, a cosmic abyss that destroys all who approach. On the other, it is a portal, a threshold to other realities, a gateway through which imagination projects new worlds. These cultural images mirror the scientific uncertainties, reflecting both the destructive power and the speculative possibilities associated with these objects. The symbolism of the event horizon itself has been especially powerful. In cultural discourse, the event horizon is often invoked as the metaphorical boundary of knowledge. To cross it is to move beyond what can be known or communicated, since nothing returns from beyond it. This resonates with ancient philosophical concerns about the limits of human understanding, echoing Plato's allegory of the cave or Kant's notion of the noumenal realm. Just as the event horizon marks the point of no return for light and matter, it also marks the edge of epistemology, the place where human inquiry must either expand or admit its boundaries. In this sense, black holes have become emblematic of the scientific enterprise itself, endlessly striving, yet confronted by frontiers that challenge its very methods. The cultural resonance of black holes is amplified by their visual representation. Before the Event Horizon Telescope produced the first direct image of a black hole's shadow, black holes lived in the imagination as abstract diagrams or simulated renderings. When the image of M87's black hole was revealed in 2019, it became a cultural icon almost overnight. Its blurry orange ring was reproduced on magazine covers, posters, and murals, celebrated not just as a scientific milestone but as a symbol of human achievement in the face of impossibility. The fact that the image was simultaneously so clear in meaning and so indistinct in resolution gave it an aura of mystery that fit perfectly with the object it depicted. Philosophers, artists, and writers seized on this moment as proof that humanity could peer into the abyss and still find meaning, that even the most inaccessible phenomena could yield to human collaboration and imagination. The influence of black holes on culture extends also into music, where composers and songwriters have invoked them as metaphors for love, despair, and transcendence. The idea of a force so powerful that nothing escapes its pull resonates with emotional experiences of attraction and loss. In visual art, black circles, spirals, and voids have come to stand in for the black hole, often placed at the center of canvases as if to swallow the viewer's gaze. These artistic appropriations reveal the extent to which black holes have become shorthand for intensity, finality, and the encounter with the incomprehensible. At the same time, black holes have prompted philosophical reflection on humanity's place in the cosmos. They force us to confront the fact that there are regions of the universe fundamentally inaccessible to us, realities that exist but cannot be retrieved or described in full. This challenges the Enlightenment ideal of infinite progress and total knowledge, suggesting instead that mystery is an enduring feature of existence. Yet rather than discouraging inquiry, this realization often has the opposite effect. It inspires humility and wonder, motivating both scientists and philosophers to push further, to probe the boundary even if it cannot be crossed. In this way, black holes act as paradoxical teachers, reminding us of our limits while urging us toward expansion. The cultural fascination with black holes also reflects contemporary anxieties and hopes. In an era marked by concerns about ecological collapse, technological risks, and existential threats, black holes sometimes serve as symbols of annihilation, of forces beyond control that swallow everything. Yet they also symbolize possibility, the idea that beyond collapse there may be renewal, that even in the face of absolute limits new forms of understanding can emerge. Science fiction has embraced this dual role, imagining black holes as both ultimate doomsday engines and as cosmic doorways to rebirth. This duality mirrors our ambivalent feelings about the future, fear of being overwhelmed, paired with hope for transcendence. In the end, black holes are more than astrophysical curiosities, they are cultural mirrors. They reflect back to us our deepest questions about knowledge, existence, and meaning. They force us to grapple with the unknown not just as scientists but as human beings living in a world that is always larger than our comprehension. The boundary of the event horizon becomes a metaphor for the boundary of thought itself, a place where imagination stretches, where art finds inspiration, and where philosophy rediscovers its role in interpreting the mysteries science uncovers. The image of the black hole, whether in equations, photographs, or works of art, stands as a reminder that the pursuit of knowledge is not only about what we can see and measure but also about how we interpret, symbolize, and share the unknown. In this sense, the cultural and philosophical dimensions of black holes are inseparable from their scientific ones, together forming one of the most profound and enduring symbols of our age. From the moment black holes were theorized, they captured not only the attention of scientists but also the imagination of storytellers. Few scientific ideas have so seamlessly migrated into the realm of fiction, becoming a staple of novels, films, and television shows. Their appeal is obvious. Black holes combine mystery, danger, and possibility in a single cosmic image. They are both destroyers and portals, both final destinations and beginnings of new adventures. This duality has made them an irresistible subject for writers and filmmakers eager to explore themes of mortality, transcendence, and the unknown. In literature, black holes began appearing not long after the concept itself emerged. As early as the mid-20th century, authors of speculative fiction were weaving them into plots, often using them as metaphors as much as physical realities. For some, a black hole was the ultimate trap, a one-way journey into oblivion. For others, it was a gateway, a tunnel to another universe or another time. This divergence reflects the dual nature of the scientific discourse. On the one hand, black holes represent absolute limits, where even light cannot escape, and on the other hand, they hint at possibilities beyond the event horizon, places where new physics might allow travel or survival. Cinema, with its capacity for visual spectacle, embraced black holes with particular enthusiasm. They offered filmmakers the perfect combination of awe and terror, a chance to represent something larger than life and beyond comprehension. The portrayal of black holes in film, however, has often walked a fine line between scientific accuracy and creative license. In some cases, filmmakers drew closely from astrophysical knowledge, consulting scientists to ensure that depictions of curved space-time, gravitational lensing, and accretion disks matched reality as closely as possible. In other cases, the black hole became a purely narrative device, a convenient mechanism for time travel, dimensional shifts, or cosmic horror. Perhaps the most famous example of scientific fidelity in cinema came with the 2014 film Interstellar, which collaborated closely with physicist Kip Thorne to create visualizations of a rotating black hole named Gargantua. The film's rendering of gravitational lensing around the black hole, with its halo of distorted light, was so accurate that it inspired scientific papers after its release. At the same time, the film indulged in speculative leaps, imagining survival beyond the event horizon and communication across dimensions, weaving science and fiction into a coherent but highly imaginative story. In this, Interstellar exemplifies how black holes serve as a meeting point between what we know and what we dream, a stage where rigorous physics and human imagination can perform side by side. Other films have leaned more heavily into the metaphorical or fantastical. In older works such as The Black Hole, 1979, the singularity becomes a place of almost mythological transformation, more akin to heaven and hell than to astrophysics. Science fiction television shows often use black holes as episodic plot devices, obstacles to be navigated or mysteries to be solved. In these cases, the black hole is less about accurate science and more about narrative function, a symbol of danger, mystery, or opportunity. Yet even in their most fantastical forms, these portrayals retain a kernel of scientific truth, the idea that black holes are boundaries, places where normal rules no longer apply. Literature has also used black holes as philosophical symbols. Writers often depict them as mirrors of human psychology, metaphors for depression, loss, or the pull of mortality. The gravitational inevitability of falling into a black hole resonates with the existential themes of human life, where some forces feel as inescapable as gravity itself. At the same time, the possibility of wormholes or bridges to other universes has been used to explore themes of rebirth, escape, and transcendence. In this way, black holes in fiction are rarely just astronomical objects, they are symbols of transformation, annihilation, and possibility. The overlap between science and fiction in the treatment of black holes is particularly interesting because both domains deal with uncertainty. Even scientists admit that we do not yet fully understand what lies inside a black hole, or how quantum mechanics and relativity reconcile at the singularity. This uncertainty leaves room for fiction to explore scenarios that science cannot yet confirm or deny. Wormholes, time loops, and alternate dimensions may be improbable or even impossible, but they remain plausible enough within the gaps of current knowledge to serve as fertile ground for storytelling. The fictional black hole thus becomes a projection of both scientific mystery and human imagination, embodying the interplay between what is known and what is possible. At the same time, the divergence between science and fiction is equally revealing. Where scientists insist on rigor and the limitations imposed by mathematics, storytellers often bend or break those limits in pursuit of narrative resonance. The event horizon may be absolute in physics, but in fiction it is often crossed, survived, or transcended. This tension is not a failure of fiction but its strength. Fiction does not compete with science, it complements it by exploring the human meanings of scientific ideas, testing them against emotional, ethical, and symbolic frameworks. By imagining what might lie beyond the horizon, stories remind us that science itself is also an imaginative enterprise, one that seeks to explore what has never been seen. In the end, black holes in film and literature are cultural experiments with the unknown. They invite us to confront the abyss not only with equations but with narratives, images, and metaphors. They show us what it might feel like to approach the edge of knowledge, to fall into darkness, or to emerge into something new. Whether depicted with scientific precision or artistic license, they remind us that imagination and science are not separate realms but overlapping modes of human curiosity. The black hole on the screen or the page is not the same as the one in the sky, but both draw us toward the same horizon, the place where the known gives way to mystery. And in both science and fiction, that horizon is never the end of the story but the beginning of a new kind of exploration. Black holes are more than astronomical phenomena, they are thresholds that mark the limits of both the universe and human understanding. Over the course of centuries, our perspective on them has shifted from speculative musings about invisible dark stars to precise mathematical formulations under general relativity, and finally to direct observational breakthroughs with telescopes and gravitational wave detectors. At every stage, the question of what lies beyond the event horizon has haunted both science and imagination. Yet despite remarkable progress, the core mystery remains. The horizon is still a veil we cannot lift, a barrier that even the most advanced theories struggle to penetrate. Looking back across the journey through black hole research, certain themes become clear. We know the event horizon marks a point of no return, a boundary where space-time bends so strongly that escape is impossible. We understand that inside, according to classical relativity, lies a singularity where density becomes infinite and physical law collapses. We know that black holes are not entirely black but radiate faint energy through quantum effects, slowly evaporating over timescales longer than the age of the universe. And yet, despite these achievements, we are forced to admit that our knowledge remains incomplete. What happens to information that crosses the horizon? How does quantum mechanics reconcile with relativity in the heart of a black hole? Does the singularity truly exist, or will a theory of quantum gravity resolve it into something else? These questions remain unanswered not because of lack of imagination, but because the boundary itself resists access. The inability to answer these questions is not a failure but a sign of the depth of the mystery. The event horizon is more than a physical surface, it is a reminder of the limits of inquiry itself. In science, as in philosophy, frontiers are necessary. They drive us to expand our tools, to refine our theories, and to look at the universe with new eyes. Black holes, more than any other objects, challenge us to accept that there may always be aspects of reality beyond our immediate reach, yet also compel us to keep searching. The paradox is that the more we learn about black holes, the more mysterious they become. Each discovery, whether Hawking radiation, the detection of gravitational waves, or the first image of a black hole's shadow, opens new questions that deepen rather than diminish the enigma. The cultural and philosophical weight of black holes also adds to their significance. They are not just astrophysical puzzles but symbols of human limitation and aspiration. They embody the tension between what can be known and what lies forever hidden. The event horizon is both a scientific boundary and a metaphorical one, a place where reason, imagination, and creativity converge. In this sense, the mystery of what lies beyond the horizon is not only a scientific problem but a cultural and existential one. It speaks to the human condition itself. We are beings who strive to know, even in the face of the unknowable. For now, the question of what lies beyond the event horizon remains impossible to answer. Our current theories break down at the threshold, and no observation can penetrate the veil. But impossibility is not the same as futility. Science is built on the history of solving what once seemed insoluble, and the pursuit of the black hole's secrets will continue to drive innovation. New generations of telescopes, new models of quantum gravity, and perhaps new ways of conceptualizing reality itself may one day illuminate the mystery. Until then, the event horizon will remain both a literal and symbolic frontier, a place where curiosity meets its greatest challenge. The horizon of a black hole is thus also the horizon of our knowledge. To look toward it is to confront the edge of understanding, but also to be reminded that the unknown is what keeps science alive. The darkness beyond the event horizon is not merely a void but an invitation, a call to continue exploring, imagining, and questioning. Whatever lies there may remain hidden for now, but the pursuit itself enriches our view of the cosmos and of ourselves. In that pursuit, we find not only the mystery of black holes but also the essence of human inquiry, the refusal to stop at the horizon, the determination to look beyond, and the recognition that even in the face of the unknowable, there is meaning in the search.